Welcome, everyone, to today's Passive House Alberta Building Better in Alberta webinar series, sponsored by the Alberta Eco Trust. My name is Frank Crawford, and I'm the Education Committee Lead for Passive House Alberta. Today, we'll hear from Michael Ridler, the General Manager and Technical Trainer for Eden Energy Equipment, all about phase change materials and how they can be used in domestic hot water and other systems. First, I would like to thank the Alberta Eco Trust for their ongoing support. It is very helpful in allowing Passive House Alberta to continue their work. As always, you can place your questions in the chat box. However, since it is we're up to 20 people, so if you want to ask your questions during, feel free to put them in the chat box or unmute, or if not, I can ask them for you at the end. So with that, I won't take any more time. Take it away, Michael.
All right. Well, thank you very much, Frank. I really appreciate everybody making time today to join me for this discussion. I'm going to go through a PowerPoint presentation today. If you guys have any questions, feel free to throw them in the chat room, and Frank will be happy to answer them. We can also do a Q&A at the end. Happy to dive deep into this. So we're gonna cover a fair bit of ground here as we sort of talk about phase change and what does that mean. And really, for me, the most important thing with phase change is the ability to sort of unlock grid resilience with thermal energy storage. And we're not going to, talk about theoretical. We're going to talk about how we can do that and how we can do it in a really meaningful way.
Yeah, I'm muted
So
anyway.
as we talk about some of the challenges that we sort of face with the electrical grid, because really that's where I want to drive this entire conversation, is we have a bit of an intermittency problem. I travel across Canada, so I'm based in Toronto, but today I'm talking to you from a boardroom in Ottawa, and in 2 weeks' time I'll be in PEI, and I've just returned from Vancouver. So when I speak, I try to speak to the communities that I visit and spend meaningful time in, and the challenge we face is intermittency. So in Ontario, we don't really have an intermittency problem with power, but if you go to PEI, there's an intermittency problem with power, and we need to be conscious of what does it mean when we adopt certain technology, whether it's an air source heat pump or whether it's a gas tankless. What does it mean to the grid? What are the unintended consequences? And specifically, are we introducing any system challenges? And again, I don't like the word challenge. I like to look at it as an opportunity. And anytime we're looking at opportunities, I like to be focused on the unintended consequences of sort of what happens. When we talk about grid resilience and specifically thermal energy storage, we're typically focused on waste heat recovery. Like it's really large scale energy waste recovery. And this is really powerful, and we see a lot of that. And the reality is there's a big opportunity in waste heat recovery, but it doesn't always need to be quite at that industrial commercial scale. And my hope today is we can sort of dive into some of the ways that we can start deploying thermal energy storage in homes right now with no red tape, that we can actually make a difference, but not make it complicated, not add extra costs. We can do something that's meaningful and commercial right now. The reason I think there's a great opportunity for thermal energy storage is if we look at what the demand is. So if you look globally, and globally is very similar to Canada as well, 80% of our energy demand is tied up in heating and cooling and hot water. And you guys know this better than anybody. The heating and cooling loads are shrinking, but the gas loads aren't. And that's why, and again, totally preaching to the choir here, when you guys look at what you're building, a large portion of what is being built, 70% of it is still using gas for hot water, because up until now, there hasn't been a really great way to do it in a small footprint that's resilient and grid friendly. Now, I do want to point out that my intent in my conversation today is not to say don't use gas. I'm in the horse race, but I'm not picking a horse. I'm the heat pump guy that's not going to say bad things about gas, right? At the end of the day, our job is to deliver BTUs into the home to provide heating, cooling, and hot water. And depending on where you are in Canada, it may make sense to use a hybrid approach with natural gas. And in some places, maybe you don't need it. But the key thing to think about is that thermal energy storage is going to allow us to shift our heating. So it'll allow us to choose when we're doing heating. And what that means is we can actually flatten the energy curve. We can reduce grid strain, and we can get around some of those things we talked about earlier. So for example, if you were in PEI and you have that grid resilience issue with the intermittency, if we could actually have a situation where we have enough thermal energy storage in the home that we don't have the heating running, it's really powerful in the grid. But it's also important that whatever we talk about is something we can commercially do. The other thing that's important to note is that just looking at waste heat alone, if we started looking at all the waste heat that is generated, we can generate enough power or enough heating demand, pardon me, not power, but enough heating demand that just with waste heat that we could provide meaningful heat into homes. And so a great example of that is when I toured Halifax, they've got a really, really unique thermal energy storage network. And what it is they've got district energy that they could be tapping into that using ground source heat pumps to do heating and cooling, using phase change thermal batteries to do domestic hot water, and even doing some large grid work. So the idea around thermal energy storage is not new. And if we tap into it in unique ways, big and small, you can store and capture an awful lot of energy that's actually going to exceed the total energy demand for the entire EU. Like it is very, very impressive. If I bring that back to an Ontario basis, and I'm picking on Ontario because I'm in Ontario, I probably should have included data for your area, but you guys can get that if you go to the Navius report, which is where I've pulled this graph from. Up until about a year ago, the whole idea of thermal energy storage was me, right? And I don't want to say me alone, me and my colleagues that spent a lot of time thinking about this, going, what would it look like if we stored BTUs and not watts? Well, this study from Navius Research, which is a very detailed report, I've pulled one piece out of it. If you guys Google this, you can get it. I'm also happy to supply the report to Frank, or you can look me up on LinkedIn. I'll give it to you directly. The reality is that if we deployed thermal energy storage, we can trim up to 20,000 megawatt hours off peak, which in Ontario would translate about 11 cents a kilowatt hour off of what the ratepayers pay. So that's pretty powerful. The question becomes, how do we do that? How do we deploy that? And there's lots of ways that we can do it. One of the ways that we can do it is with ground source heat pumps. A 3-ton ground source heat pump can store an awful lot of thermal energy in the ground. The best battery system we can deploy is a ground source heat pump. And I know in your area, there are a lot of ground source applications happening. A 3-ton ground loop is the equivalent in Ontario to using $100,000 versus battery electrical storage. And it's much easier to do. It's much more resilient. So there's a lot of really cool ways we can do it. But I only mention that because I don't want us to only think about phase change. I don't only want to think about industrial waste heat, but I do want to talk about phase change. So when we talk about phase change thermal batteries, what's really cool about it is phase change batteries allow us to store and release thermal energy in a very, very small footprint. And so what that means is that in a space that's up to 10 times smaller than traditional storage systems like water, we can store a lot of energy. What's more important is we can store that energy and we can hold on to it for a longer period of time. And we're going to talk about that, which means we can get selective in how we use that energy. It's also really important that we understand that thermal energy storage from the standpoint of phase change is not new technology. One of the things that we get really nervous about is, are we on the cutting edge or on the bleeding edge? And it's important. I like to be on the cutting edge of technology, just like you guys are with the work you're doing. I'm not interested in being on the bleeding edge. So the first phase change system ever done was the Dover House, and that was done in 1948. So what they did was they had 4,000 gallons of salt, and they used that salt with a solar system to heat a home for 2 years. That's significant. Now, I'm not proposing we put 4,000 gallons of salt into this application. What we're going to talk about is it's not 1948 anymore. I'm sure everybody got that memo. So right here, right now, there's phase change technology that's commercially available that allows us to get really, really innovative in a very, very small footprint. The advantage to phase change over water-based thermal storage, which is quite common and you see a lot of talk about it, is that water is only storing sensible energy, right? So in my own house, I have a very large oversized buffer tank, and I'm utilizing that just as an experiment. And the reality is I can't store enough sensible energy to do anything that's very usable in my own personal home. So yes, water has high heat capacity and it can absorb a lot of energy, but the reality is it's sensible energy. What's important is, can we store sensible and latent energy? You'll see other batteries that use sand, which are great. They take advantage of the specific heat of sand. It's very high temperature. There's a lot of different battery technology that stores BTUs and not watts, which is the purpose of our discussion today. And it's okay to use water thermal storage. It's great to use sand thermal storage, but phase change thermal storage is a great innovative way to do things. And that's sort of what we're talking about today. The other thing when we think about a thermal battery, and this isn't the purpose of today's talk, I do a lot of talks about hydronics. It's also really, really important that when we talk about thermal storage, so when we go down to that 20,000 megawatt hours off peak and we go, how can we do this right now? Well, every home in Alberta or any home in Western Canada, if we went into that area and said, we're going to incentivize taking gas boilers out and replacing them with air to water heat pumps, that is really powerful for the grid. Because as it stands right now, when we're running that gas boiler to heat the floor, which is great, by the way, I'm not saying we have to do this. It's a great way to heat a home. But if you're using a gas boiler, it really doesn't matter when it's running. The advantage to a gas boiler, especially in a radiant system, is the whole house becomes the thermal battery. Well, if you install an air to water heat pump and load shift when you're heating the mass of the building, not only are you taking advantage of a very high COP, an efficiency of up to 300%, but from an electrical grid standpoint, you can point out to your local operators, hey, listen, if you want to advocate for heat pumps, just don't say what kind. Air to air, great. Air to water, also great. We can take a boiler out, replace it with an air to water, does heating, cooling, and domestic hot water. So this is just here to point out that there are other methods of thermal energy storage that we have to think about that sort of goes beyond the water heating discussion we're having today. So when we look at the limitations of water storage, and I've already touched on this, it has a high heat loss, right? When you look at storing water in any kind of a vessel, it needs to be very well insulated. It can be hard to insulate. The other thing that's really important is that the temperature range. We have to hold the water at a very high temperature, and then we're using a mixing valve to bring the water down to a usable temperature. And so that combined with large volume, high heat loss, and the temperature ranges we need to hold it at are also things that work really well with phase change. The other thing is that phase change thermal batteries, which in this particular case, we're going to focus only on water heating, are anywhere from 3.5 to 10 times smaller than the water-based system. And that's not a range I'm just arbitrarily making up. I'm going to dig into why there is that change. So as we look at sort of the phase change advantage, the phase change advantage is its ability to absorb and hold an awful lot of heat and have significantly lower heat losses. When we look at this previous slide, you guys can probably already tell from just looking at this which one of these two devices can be vacuum insulated. The one that's tiny, the one that's large. There's a lot of reasons why we can store more energy in the phase change battery, and we're going to get to that. We're going to have a marketing piece that was applied to me by Sunet. We're going to get beyond the marketing to real world data. But if you look at this, the blue line on the left-hand side represents water, right? So when I charge a water heater like the one that you just saw, I'm storing sensible energy. So I'm going to start at a low temperature. I'm going to heat the water up very, very hot because I need to make sure it's a condition where it won't form any kind of bacteria. And then the tank itself is going to be hot at the top, usable heat, not as hot in the middle, and the bottom will not be usable heat. What's really unique about a phase change battery is that's not how a phase change battery works. So what a phase change battery does is initially when you're charging the phase change battery, and to be very clear, the phase change batteries charge themselves, and we'll get into how. The initial energy is us heating up the phase change material, which is salt. It's a salt hydrate that is NSF rated. It's completely safe and environmentally friendly. So as the salt is being heated up inside of the phase change battery, the sensible energy is being stored in the heat exchanger. And then what's happening is now we start to melt the phase change material and it's storing latent energy. So what's happening is the entire phase change battery becomes the same temperature. So in the case of the phase change battery that is shown here, this is a P58. P stands for plenty grade, not phase change. Plenty grade, which is the IP protected material that there is a patent on that phase changes at 58 degrees C. So while it's phase changing, all of the latent energy is being stored inside of the phase change battery. Now I call it a battery just because of the fact it's storing BTUs and not watts. But the biggest thing is it's just storing heat. How we store that heat is totally up to us. The units that we're going to talk about and I'm going to dive into are designed to replace water heaters. So they have a 3 kilowatt element in the bottom of them that allows it to charge itself, and you can charge it off peak, on peak. But the key thing is the very tiny footprint, which we're going to get into. You could choose to charge it electrically. You can charge it with solar. You can charge it with an air to water. You can charge it with a boiler. We could spend an entire hour just talking about scenarios of how you could charge it. But the key thing is the very high energy density and the very low standby losses. So when you look at a phase change battery, the standby loss is going to be anywhere from 0.4 to 0.8 kilowatts per hour. Whereas if you look at a traditional water heater, it's going to be a factor of like 1.5 to 2.5 kilowatt hours. Because again, the phase change battery is very compact by its engineering, which makes for a really well insulated system. Because it has 50% lower standby losses, it also means that the energy is available when you need it. What's really unique about a phase change battery is you actually do want to make sure that you pipe it properly and it's thermally trapped, because the standby loss on the thermino is the piping, not the unit itself. If I put my hands on it, it's not going to be hot. One of the biggest examples we have for phase change, so at Eden, we have a live fire lab. We send units out to test sites and we bring them back. We had a unit that came back to us, and for a week it sat in our warehouse and was still hot. That's the biggest testament to phase change. When these units are made in the factory, the phase change material is put in hot and needs to be poured into it. They need to let those phase change batteries sit for a week before they can ship them, because they actually need it to solidify. The manufacturing process shows the power of what you can do with phase change. It holds onto the energy much longer. The other thing that's really unique about this, and these are UK numbers in this particular case, so I apologize for that, but the numbers actually still do work. If you were to look at the cost to store 14 kilowatts in BTUs versus 14 kilowatts in watts, it's a totally different animal. Now, I'm not advocating that we should be doing one or the other. We should be doing both. As it is right now, if we put a solar PV system in, we can put a power wall in, and I apologize, I don't know the PV brands very well, but we can put electrical battery storage in. But the nice part about the phase change batteries, again, because we can choose when we're charging it and it holds onto the energy, we can also choose to put a BTU battery next to the electrical battery, and we can do it for a quarter of the cost. We also don't have any of the potential health and safety concerns of flammability. How do we do it? How do we get it wired? Putting a thermal battery in is just like putting a water heater in, cold in, hot out. But the argument here is that both are a really, really good application as we get a solar PV. So I've covered a lot of this already. My PowerPoint, as I say, is just here for your benefit. I'm just sort of talking as we go along. The biggest thing to note about a phase change battery is its resilience. You think back to the Dover house in the 40s, the one I showed you, just so we all have the peace of mind of it's not new technology. This particular unit that I'm going to show you, there's over 37,000 of the systems installed. There is a third-party testing that shows that these units are going to cycle up to 40,000 times. So when you look at life expectancy of a phase change battery, one thing you want to make sure is there third-party testing on the phase change media that it is in fact going to phase change more than 5, 10, 15 times, which sounds ridiculous, but believe it or not, you do actually want to ask that question of what is the third-party testing. If you look at a phase change battery that can phase change 10,000 times, we assume 210 liters of domestic usage for a family. It basically means the battery is going to last between 20 to 28 years. And what's really unique is the equipment comes with your
Michael, your internet connection is getting a bit slow. Do you maybe want to turn off your camera for a sec and
So
see
I
if
think
it
I've
picks
covered the
back up?
rest here. The other thing that's really important about phase change batteries is they don't have any moving parts. None. Doesn't make any noise. There's no venting. There's no gas line. It's literally just a heat exchanger that's encased in phase. Pitch a particular brand, you guys. My intent is to pitch a camera. Let me see if I figured it out. I think I got it. Let's hopefully that's a bit better, guys. I don't know why it was acting up. Am I a little bit better, Frank?
Yep, you seem good now.
Okay, sorry guys. So as I was saying, there's no moving parts. And again, my point is not to get into a particular technology. I want to pitch the idea. I'm happy to get into the weeds of an actual product and show you what it looks like inside. That's just not what we want to do today. So as we sort of walk through what it looks like, and remember earlier where I said it's 3.5 to 10 times smaller, this is where it's really important. So what you're seeing here is phase change batteries that operate at different temperatures, everywhere from 5 degrees Celsius and lower for that matter, upwards of 89 degrees Celsius. The energy density varies anywhere from 3.5 to 10 times. The only thing I'm going to leave with you here is that you can actually buy phase change batteries that store BTUs for cooling, not just BTUs for heating. So that's an important distinction to know. As we look at it, this is the different types of units that are typically available. And what I mean by this is commercially available. You can buy it now. The unit on the left-hand side, which is a 20-gallon phase change thermal battery that would use for a domestic hot water application, is literally the size of a microwave. So when you're trying to figure out what it looks like, that's what it looks like. So the footprint is the footprint of the microwave. The height is a microwave. What's really, really cool is the unit next to it, which is 40 gallons. Total height is 23 inches. The Thermino 80, which is an 80 gallon, which is equivalent to 300 liters of domestic hot water, that unit is 39 inches tall, but it's still in that microwave footprint. And on the right-hand side, I'm just making the point, there's a bunch of commercial options as well. There's a bunch of different variety, but the key thing is small size of it. So here's a really interesting application. Sunamp supplied me with this photo. It's the one that Sorel did in Quebec. So this is a whole bunch of the Thermino 80. So if we go back, this is the microwave size unit here that's 39 inches tall. They put an entire bank of them into a system that's 2.1 million BTUs of domestic hot water. It can do off-peak charging. It has 50% less standby losses. So it's really powerful in domestic hot water capabilities they can provide. This is an actual schematic that shows what a phase change battery is doing in our live fire lab. So this data was pulled off our phase change battery using a Measurement Canada certified meter. So what you're seeing with this orange line, water drop. The orange line.
Michael, why don't you just turn your camera off? You're still
coming off the battery. Domestic hot water at 1.75 gallons a minute, which is green line over an hour. This is latent energy. Energy you're seeing is 130 degrees of latent energy, and then after an hour and 50 minutes, just dumping this thing, it starts to finally pull sensible energy out of features.
Michael, why don't you turn your camera off? You're still cutting in and out a bit.
I'm going to show you a couple of projects here. Sorry, my internet hung up on us for some reason. So one of the really cool applications that we've seen is this one. So this is a project. This project is an application where they had 273 flats. And what they ended up doing was actually connecting the phase change battery in a system with the large heat pump. Because again, they don't care how you charge it. You can charge it electrically, or you can charge it through another means. It really doesn't care. So in this particular case, they were able to reduce the hot water bills by up to 66%, take losses. This one is particularly cool to me. This is a 101 unit project in Troy, New York, where they wanted to retrofit the domestic hot water to take advantage of a heat pump. As you guys would all know, this can get complicated because 101 units is a lot. What they ended up doing was they used a single 4-ton water furnace heat pump tied to 3 Thermino P43s as preheat for the gas. They were able to reduce the gas consumption by 23% because instead of the water coming in at 38 to 74 degrees, depending on what time of year it was, it's now coming in at 86 to 106 degrees because we're preheating using the GEO, which results in a 23% reduction in their gas usage, and obviously all the greenhouse gas reductions that come with it. So the photo here on the left is a little water unit, and then here on the right, you can see behind it. Very easy, right? It's 2 connections back to the water to water, and then 2 connections for the hot cold domestic hot water. This is the one that's pretty cool. This one takes you to about it. I got asked years ago, would you use PCM on a gas boiler? And I was like, I'm not sure that I would. Foolish statement by me. If we can actually install a hot water device that's always condensing and has 50% lower standby losses, it's going to result in a significantly lower gas consumption, which is good, right? If we can use less gas, it's always productive. So NY Certa did this study. They were able to reduce the gas consumption by 50% simply by taking an indirect out and putting a phase change battery in its place. But to me, the holy grail statement of what we can do with phase change batteries is what you see in this picture. Phase change for domestic hot water, it can fit anywhere. This is the equivalent to a 40-gallon water heater installed underneath a countertop. Personally, I would have put a door on it, but it's got a compact size. It doesn't need to be overheated. It doesn't need venting. It doesn't need a gas line. It's not going to air condition the space. It's a box that holds phase change and a heat exchanger. It's a really, really powerful statement when you see pictures like this. As people who are designing mechanical systems, you can understand without me explaining the value to a builder if you can do that. but this photo illustrates it much better. So this is an installation photo. Left-hand side is an electric water heater. Right-hand side is the equivalent sun amp, right? This is the power statement. Now, this is obviously a retrofit, but you guys start developing apartment buildings or stacked townhomes and go, which one of these can I put anywhere? Under the stairs, under the vanity unit, under the drop leg of the air handler. Like, the big power play for this is the compact footprint. So it's really cool from a domestic hot water standpoint because it represents a consistent and predictable load for the utility. It's a 3.05 kilowatt element, which means a 15 or 20 amp breaker, depending on what code compliance allows for you, if you look at that 80% rule. So it's got less electrical consumption than other devices because of the 50% lower standby loss and the fact it holds onto the BTUs. You can also take advantage of off-peak charging, which is really, really powerful. Don't generally pitch that as the first play. The first play is it has no moving parts, it doesn't store water, and you can fit it anywhere conveniently, and it's easily retrofittable. Obviously, no venting is great, whether it's a gas tankless or whether it's a heat pump water heater, both great technologies, but sometimes you just simply can't do that. And more importantly, I met with a contractor this morning. This is a common theme where a heat pump water heater was put in, and that heat pump water heater did not get ducted, even though the contractor had asked for it to happen. He got pushback. And then, of course, you can imagine what happened is the total heating load was like 13,000 BTUs. Well, it was a problem because the heat pump water heater didn't get installed properly. So we definitely want to be conscious of, if you install stuff properly, you don't have these problems. But sometimes you just simply can't, because of the envelope, be poking holes through the envelope. So there's some pretty unique advantages to it. The other thing is you can start to get in some really creative ways where you can store a significant amount of energy using solar systems throughout. You can also do really cool things like integrating them directly with heat pumps so that we can charge the phase change batteries off peak utilizing an air to water heat pump. And some of the new things that we're seeing is a new technology that's now available in Canada where it's an air to air heat pump that's using phase change for thermal storage as well. This photo here is mainly for the benefit of you guys that want to dig a bit deeper. This was one of the first phase change systems I saw. This QR code will take you to the video. So what this is this is a home where they have a micro CHP. This is a research site. Normally it doesn't have this much stuff on the wall. They got a lot of sensors, but what it is a micro CHP producing electricity for the home. And I'm standing next to the 300-liter equivalent of a phase change battery. And they're using that waste heat to provide the domestic hot water for the space. So it's a really cool application for phase change. So that's my run through. That's sort of my broad overview of what is phase change, how can we use phase change. But the really big photo I kind of just want to leave with you to percolate on is this one right here. This is the power where we can go into existing homes, we can utilize phase change, and we can do it in a really meaningful way from a domestic hot water standpoint. So I'm going to turn my camera back on here.
Yeah, we'll see if you might get.
I'm sharing for 1 second and see if I have any questions about it.
Yeah, I'll open up to questions. Although I think your internet's still a bit scratchy, so I might better turn your camera back off, Michael. And as much as we like talking to a voice, we like hearing the voice better.
I don't know if you're muted, Frank, or if it's on my end.
Yeah, I think it's on your end, Michael.
Okay, it'll get better here in a second, I think.
Okay.
Sorry, guys.
That's okay. Yeah, so any questions, I guess, for you, feel free to unmute. If not, maybe Michael, if you have something available, maybe show up kind of maybe the costs or how you would actually run through installing one of these in a unit to kind of to show the kind of cost comparisons and the space savings.
Yeah, so when you look at space savings between utilizing phase change versus a tank-based system, it's pretty significant. If you look at cost of doing installation, so if you look at the install cost of a heat pump water heater or a tankless compared to a phase change battery, the install cost is the same.
Interesting. Yeah, and that's so it's because you're, I guess, using a smaller space, smaller material, but the equipment's and just simpler to install.
I apologize, Frank. For some reason, we've got a terrible connection just kicked in every now and then.
Yeah, here I'll turn your video off, and it got better before. So yeah, I guess maybe do you want to explain a little bit more of the details on how you get that similar cost comparison is because it's a smaller unit and it's installed simpler, or just that's what the equipment seems to cost these days?
Yeah, no, that's a great comment. Thank you for clarifying. So when you look at the cost of the phase change battery, whether it's a 40, a 60, or an 80, the actual phase change battery itself will be more money. The statement that it's the same install cost as a heat pump water heater or a tankless doesn't come from me. It comes from the installers. So specifically, when you compare to the heat pump water heater, the cost of the equipment is not far off between a heat pump water heater and the phase change. But obviously, there's a whole bunch of things that don't need to happen. You don't need electrical grid upgrades. You don't need to be venting into the outdoors. It's a very simple installation. It also doesn't need to go into a big mechanical room. So you have the option of putting it in an easy place. When you look at the tankless, it's the same conversation. There's no gas line, there's no dual trade, there's no venting. But really and you guys will know this well, the big thing is from a builder standpoint, if you guys do any kind of stacked townhouses, I'm sure you've had this where it's like, okay, it's great what we're doing here. How are we venting this equipment? Right? Or better yet, we're going to put the mechanical equipment in the crawl space. Where are you putting the water heating device? Right? And you have these struggles, which is why I feel the bulk of the domestic hot water systems remain gas, because the easiest path to domestic up until now has been gas. Like, how else are you going to give somebody 2.5 gallons a minute for a family of four? In the past, it's been a gas-based solution. So it wasn't always the case that phase change install costs would be the same. It's just been, hard work and more market adoption over the last 4 years where it started to become more and more parallel. The only place it's going to be a lower cost installation would be an electric water heater because they're very, very cheap. Electric water heaters have their advantages, obviously, and their disadvantages. But the biggest thing is spaces are getting smaller and smaller, and which one can we fit easier? So depending on what you're building, it won't make sense, right? It may make sense to use an electric water heater because it's low cost, you've got lots of footprint. But if you're in a scenario where you need the footprint, you need high performance, it's definitely a way to do it.
Excellent. And how does it achieve the lower standby losses? Is it just better insulation, or how does that occur?
Yeah, so that's a great comment. So the lower standby losses are in the nature of the vacuum insulated insulation that goes around the unit and extensive engineering. So the unit itself, if you were to cut it in half, so if you go on our YouTube channel, so if you go to Eat Energy Equipment on YouTube, there is a 60-second video that shows you the inner workings of this unit. I would normally share the video, but for whatever reason, the internet gods today have decided we're not going to have a great connection. So I'm not going to bog it down and play a YouTube video for you guys. But you can see what the inside of this unit looks like. So it is a specially engineered box that has vacuum insulation all the way around the outside of it that allows it to hold on to the heat. The only Achilles heel to the unit, it's actually not an Achilles heel at all, is that it's the one scenario where you do want to insulate the piping going to it, right? We all see like, hey, insulate the lines off your water heater. Well, the reality is the phase change battery, the standby losses on it is the piping, not the battery. So if you don't properly install it, and it's not rocket science, right? It's thermally trap it like we should be doing and insulate the lines. It makes a big difference. So
Excellent. And then is there a pump in it, or does the water pressure just go through it? What does the rest of the system look like using the phase change batteries?
yeah, great comment. So just think an electric water heater. That's the exact same things you need. So there's no pump, there's no extra stuff. It's a self-charging unit. It's just a smaller load, right? 3.05 kilowatts. There is no pumps required of any kind. So water comes in at 50 degrees, water comes out. You have to have a mixing valve on it. Like, it will be hot enough that you can scald yourself. As much as it's much, much lower temperature, we have to be conscious of we can still burn people with it. But installation wise, there's no learning curve. It's just a much, much smaller footprint. So you still need a relief valve. You still need an expansion tank, just a very small expansion tank, one of those baseball size expansion banks. And you would also want to make sure that you have a mixing device on it. And then just a pressure reducing valve if you're in areas where you get really, really high pressure. But it is literally a heat exchanger, phase change material in a box. Now, it sounds very dismissive. The people that developed the IP around this have spent a lot of time developing this IP, but in simple terms, from what we care about, it's a heat exchanger, it's salt, it's inside of a specially engineered box, and it's NSF, right? It's environmentally safe, it's human safe, etc.
Excellent. Any other questions from the audience? Feel free to unmute. How since in Calgary and Alberta we have pretty cold incoming water, like 3, 4 degrees Celsius, it can still uh, increase that water enough.
Correct. Yeah. So at the end of the day, it is a simple math formula, right? Depending on how cold your water is going to come in, you'll have less capacity out of it, whether it's an electric water heater or whether it's a phase change battery. If you can share some actual examples, we can do some calculations on what that looks like. But it's just an inertia conversation, right? And it's the same thing with a gas tankless. If the water's coming in colder and the tankless is designed to do 4.7 gallons a minute at a 70-degree rise, well, if it's an 80-degree rise, it's not 4.7 gallons a minute. It might be 3. So it's the same physics, I guess, is the answer.
Okay, excellent. Thank you.
Dan saying time of day of pricing electricity would make this. I just didn't see the rest. Maybe you can see it, Frank. Oh, here it goes.
Uh, Dan, feel free to unmute. I'm not seeing that question right now.
Yeah, sorry. I guess like I in Alberta, maybe well in Calgary, we don't have time of day pricing for electricity. So heating a unit at the middle of the night is this expensive as heating in the middle of the day, which, probably isn't the best option. But I guess in Ontario, this sort of a unit might be more cost effective because you can heat it or store the energy when electricity is less expensive. Is is that what I'm understanding?
Yeah, Dan, that's a great comment. And so I have to be careful of my answer here because the reality is that heating it off peak is kind of whip-de-doo. I got to be careful. I like the idea of it, but you're exactly right. Like, so you heat it off peak. Who does that benefit most? So the reality is, does it benefit the homeowner for sure? But who does it benefit more? The grid, right? The grid's ability to say, okay, what's the easiest way for us to deploy thermal energy storage? It's exactly as you just said, but utilizing it from the standpoint of being able to load shift the domestic hot water in 1,000 homes. What does that look like? And what does that take? Well, the reality is it doesn't take very much. The draw to the equipment is the resilience, the reliability, the 10-year warranty, and the fact that it's a quarter of the size. You start getting into places like Halifax and PEI where they have challenges with their grid. It's very, very powerful. You go in Ontario with time of use, you're exactly right, Dan. We charge this thing off peak, use the 4.5 cents a kilowatt instead of the on peak rate. It's very powerful. But everywhere you go with thermal energy storage, it's good for the grid. And to me, that's what we sort of need to look at.
Thank you. All right, another question, maybe just to elaborate a little bit, Michael, on kind of the difference between B2s per hours, batteries, and watts. And then, Stefan, you can ask your question afterwards.
Yeah, so I saw a question pop up that I think is related to it of like, hey, could we use this for heating? So let's sort of dive into that and answer Frank's question at the same time. So the thermal battery doesn't care what you use the BTUs for, right? So if you look at the Thermino 80 at roughly 48,000 BTUs, you start looking at a home that's got low heating loads. Like some of the heating loads I'm seeing are anywhere from 13,000 to 9,000 BTUs. Now, obviously, those aren't custom big homes. I'm sure you guys probably challenge each other to build these homes with these loads all the time. What it means is that you could go into a home, store those BTUs inside of a phase change battery, and utilize it for load shifting in a hydronic application. So there's a lot of heating applications that are happening, and they certainly can be effective. But I like to draw it back to the reality is the bulk of where we can do the work is actually on hot water, in my humble opinion. But there's some pretty cool innovations in Canada that are coming, and I can maybe talk about it in a different talk with you guys because I can share a particular air-to-air heat pump that is utilizing phase change for air-based heating, where they're able to turn the compressor off for 3.5 hours because of how they're using phase change. So yes, it can be used for heating. I think it's probably a more detailed conversation and presentation, and I do have one where we can sort of dive into, okay, let's move beyond hot water. How can we use phase change right now in heating? And the answer is you can do it a lot of different ways. Hopefully that helps, right?
Yep. Yeah, Stefan, why don't you ask your question? And then, yeah, if Martin, you wanted to have any follow-up, feel free. Go ahead,
Sure.
Stefan.
Thanks so much. Michael, you mentioned the benefits of using this phase change battery for on-grid situations, but what about an off-grid project? And especially an off-grid project that might be unoccupied for maybe like weeks at a time during the winter.
Yeah, so that is a great comment. So the second system that I ever saw was a sun amp on a 5 kilowatt solar PV system. And there's actually some really good case studies on SunAmp's website, specifically around the SunAmp on PV. And you can do some pretty cool things with it, whether it's solar PV, whether it's a micro CHP. Really, it doesn't care how it gets its charge. I believe the latest case study that was done was a 2.5 kilowatt array charging the SunAmp phase change battery. I have asked minds much brighter than me about using solar thermal. So Dr. Steve Harrison, I encourage you to look him up. I went to him. He's a leading authority on phase change globally. He's also a leading authority on solar. And I said, Steve, I've been thinking about charging the phase change battery with solar thermal, but he made a very, very technical, articulate case for Mike. Solar PV is less money, more resilient, less BS, and you can phase change the battery very easily. And there's lots of case studies pointing to that. So any kind of off-grid application is not niche. If you look at the case studies available, that's where they're driving a lot of their discussions beyond the traditional water heating applications that are happening in the tens of thousands. And anything I've talked about, if it's helpful to share case studies, if you connect with me on LinkedIn, I'll gladly bomb your inbox with nerdy stuff on a variety of topics.
Thank you. Yeah, maybe Michael, just go back to kind of the BTUs versus watts and maybe sensible versus latent energy, just to help clarify how those different things work.
Yeah, so when you look at the Thermino, which is the unit that I shared those photos of, just think of it as a box that's storing BTUs. So in the case of the Thermino 80, it would be a situation where it is the equivalent to 80 gallons of domestic hot water usable heat at 58 degrees C, or it's the equivalent of 4 tons of continuous heat at that temperature. So if you remember that graph I shared, once we pull the sensible energy off, all that latent energy that's been stored in the battery gets drawn off. So it's coming off at that same temperature. So, every unit has different BTUs capacities. If you remember the big guy that I didn't even talk about in the slide where I showed different sizes, that unit is the equivalent to 300,000 BTUs of thermal energy storage at 58 degrees Celsius in this particular case. There was a question about, could we use this on data centers? I'm connecting dots here for you. A great use case for these phase change batteries is exactly that. We connect them up to a data center. We maybe use a commercial battery. We store the energy there. We can store the equivalent to 1.2 million BTUs of thermal storage in smaller space than a sea container, right? So it's very impactful for how we can store that energy. Really, what's unique about it is because it stores latent energy, it just means you've got the same temperature all the time, right? You're not like, okay, for the first 20 minutes, I've got 80 degrees C, and then for the next hour, I've got 40 degrees C. Once you draw off the initial sensible energy that's stored in the heat exchanger in the media, the remaining latent energy is the same temperature, which is that 58 degrees C. I would also say that as much as I'm talking about 58 degrees C, they come in all flavors. There's cooling units at 5 degrees, there's 43, there's 54, there's 58, there's 89. There is a phase change for everything. It's kind of like ice cream. What flavor do you like? But the 58 degrees C is just something we can use in so many applications.
And sorry, as I'm understanding then, really the reason that it's the same is because it's the temperature when the phase change material liquefies and solidifies. So it's the same temperature when it's changing that phases, and that's why you get much more energy, because it's changing the phase. Like when water melts, it goes from solid to liquid at 0. You're just picking a salt that changes from liquid to solid at 58 or 43 or some other different temperature.
Right. So SunAmp in particular has IP that allows them to phase change at very particular temperatures. The nice part is it's usable temperatures we can produce anywhere, right? So waste heat off of a data center, we can marry a phase change battery that melts, as you've rightly pointed, at the temperature the data center uses. We have an application with a manufacturer who has waste heat that's not usable heat that they can store, except for the phase change battery. So we're going to store the heat in a phase change battery, and we're going to use it to heat the warehouse. Like, there's a lot of different applications. What's cool is, Stefan made a comment earlier. I believe it was him that talked about PV. I could be totally wrong, but he could come back and say, Mike, I need something that melts at 43 degrees C. Okay, no problem. It's a P43. So the P is plenty the 43 is the temperature.
Very interesting. Any other questions? Just looking through.
Yeah, and obviously, if there's questions afterwards, phase change is a complicated topic. We typically spend a few hours on it, but I'm trying to be respectful of time and leave time for questions. I work with a whole variety of different organizations. I'm happy to keep talking with you guys. You can connect with me on social media. I'm happy to come back and do a follow-up and get into some actual real-world scenarios. And
I guess
I certainly enjoy these interactions.
Sorry, I guess my question was, how tricky is it for the installers? Is it a plumber that installs it or a hydronic technician that installs it?
Yeah. No. So if you're just doing the domestic hot water crossover, it's just a plumbing unit, right? So it's just cold in, hot out. Again, remember, expansion tank, relief valve, all the normal things. Like, your plumber's not going to struggle with it. If you're doing it in a hydronic application, there is a 4-pipe unit. So it's still the same conversations. Just 2 of those pipes will be your domestic connections. 2 of those pipes will go to your air to water, your boiler, your waste heat. And if you're in a solar PV application, it's just a water heater, right? So it gets wired up, comes off the solar PV system. It's not rocket science. It's very simple. The way the unit charges itself is it has a dry contact on the top of the unit. And so basically, when we install the water heating unit, cold pipe in, hot pipe out, we put a jumper on the control, which is the only thing that's on it, and it charges itself only if it needs it. So when you think about some of the applications on how you want to use it, a simple contact closure on the top of it would allow the unit to come on, but it's only going to do it if it needs to. So I really like the KISS method, the keep it simple, stupid method of controlling it, which is very slick.
Thank you. Question: If we kind of apply these to kind of the missing middle multifamily typology, where you have like multiple units in a 4-plex, 6-plex setting, would it be, I guess, more cost effective or more energy effective to have one larger phase change material or smaller ones located throughout the building?
Yeah, that's a tough question. I mean, the fun part is I can answer it different ways, right? So it depends. If it's you own it. So I've got a project right now, right? And so what it is originally it was going to be owned. They were going to sell the units. So we were doing individual phase change batteries in the suites, right? And then it became, because of what's happening, I don't know if you guys heard in Ontario, there's a bit of a housing crisis. Has that word gotten out of Ontario? So they went, okay, we're going to pivot. We're going to do a rental instead. So now what we're looking at is doing a centralized unit. But really, there isn't any right or wrong unit. The decentralized is convenient, right? The hot cold is right in the suite. And the nice part is, because it's so small and you don't got to figure out how am I venting it, where's the gas line coming from, where am I putting it? Like, it intrinsically removes all the difficult questions. And then it becomes, what's the faster, easier install? So my gut is put it in the suite. You can then sell the unit later, like not the phase change, but you could sell the townhouse or whatever it is later, or if it's a condo. It gives more resilience, but you could argue either way. Like, if you put 3 experts on domestic in the room, we'd argue till we're blue in the face in different approaches. So there's no wrong answer, I guess, is my long-winded answer.
And it would probably come down to how well insulated your pipes are, and it's more the distribution time length than the location of the tank, I guess.
Yeah, all things being equal, I think I would want to put it in the suite, but I'd have to know more, right? Is it 20? Is it 40? Is it 100 units? So.
Okay. Do you want to talk, I guess, a little bit maybe about combining it with an air to water heat pump and what systems can look like for that if you wanted to do domestic hot water heating and cooling?
Yeah. So I'll touch on it lightly. What I would say is we could do a future webinar where I share some mechanicals when we get deep into it. So the advantage of using an air to water on a phase change battery is the air to water would basically pipe up to the phase change like it's an indirect tank, if that makes sense. You have to be careful which model you use. So for example, you can't use the P58 currently. All of the residential air to water equipment in Canada cannot get to 58 degrees Celsius. I don't care what you read in their manuals, it can't do it. Now that's coming very soon because certainly in Europe they can do it no problem. So we would do a P54 and it would be piped up in such a way, same as you would do an indirect. So if you guys are familiar with how to do an indirect, it is the same stuff. The nice part about it is we do have some selectiveness on when we charge it, right? Because it's so energy dense, because it holds on to that energy, we can be selective of, okay, we can actually charge this thing, utilize the domestic hot water when we need it, but we get to choose, to charge it when we want. So if they have a long heating demand, it's okay. They're still going to have hot water. They're not going to run out.
Excellent. And I guess you didn't talk maybe about controls. Is there embedded controls in the unit, or is it agnostic to whatever controls you want?
Yeah, I like that. So that comes back to the KISS methodology of the controls. It's just a contact closure. So there's no moving parts of any kind in the unit. The video on the YouTube channel for Eden Energy Equipment, EDEN, for those looking for it, it'll give you a good blowout of what it looks like inside. It has a sensor. It's a 10K sensor that runs the entire length of the phase change thermino that allows it to phase change. So what that sensor does is it tells the element in the bottom of the unit, if you're using the element unit, i.e. hot water, if the sensor sees that it needs to charge, it's going to tell the element to come on. It only comes on when the dry contact on the unit is closed. That's the only control strategy. So the cool part, or the hot part, sorry, I got to get this right. The hot part about it, as people would joke, is that if you wanted to use some sort of off-peak charger or time of use demand control, you just the right when the contact is. So the only install issue we've so.
You cut out a bit there, Michael. Can you repeat that?
Yeah, sorry, Frank. I saw at the end my network went bad. So control-wise, it's a dry contact. It's super, super easy. And if you close the dry contact and it's charged, it's not going to charge itself. It's smart enough to know not to.
Okay, interesting. Yeah, so it's nice that it's agnostic and that you're not locked into certain proprietary items and have lots of options.
Yeah, I love that as well.
All right, just looking through. Anything else? Anyone else want to unmute and ask? If not, we still have a few more minutes, or we could end a minute or two early. If no one else has anything, see if I can come up with more questions too.
Yeah, sorry, I apologize that we've got a bit of a spotty internet. That sometimes happens out of our control.
Yeah, it's technology. Always knows it's going to change and not always work correctly. It's about the only thing we're certain about. Alrighty, well, yeah, I don't have any more questions at the time. Yeah, it's good to see all the different options, and it's nice that it's now readily available, and it's not too tricky or nothing too fancy, and doesn't seem like you need any more training for contractors to put it in. Is there, I guess, where would we buy it? How about that? If we're going directly to the Sign app, where do we buy it? Is there like a national network of suppliers? Do we go through you directly? How's that work?
Yeah, so right now the way that SunAmp is coming to the market is through distribution. So you would buy it through a contractor like you traditionally would. So it's nothing special. You go to your plumbing contractor and say, okay, we'd like to have a SunAmp, and they would reach out to their local wholesaler to get the product. So it's pretty traditional in that way. The products are stocked in Canada. I have been asked the question, how do we get parts? And I just remind you, there are no parts. That's kind of the easy one to answer. There are no parts. Unit comes with a 10-year warranty. There isn't any maintenance per se. Like SunAmp would definitely say there's no maintenance. We push back obviously on certain things of like with anything, you gotta treat it kindly, whether it's a tankless, an electric water heater, or whatever the case may be. It's designed for water, not mud, I guess would be the answer to that. So, but yeah.
A question from Carol. So I guess reiterate again that the sun app itself doesn't create the energy. The energy comes from wherever you want. So it could be from a wind farm, solar, anything that you can basically pick where the energy comes in, and it just stores it efficiently.
Yeah, so you have two choices. You can generate the domestic hot water, if we just talk hot water for a second, you can generate the domestic hot water in the unit with the built-in 3 kilowatt element. Or you can charge it externally with air to water, ground source, solar PV, whatever. But they do have the ability to charge themselves as well. So it is as simple as heat pump water heater goes away, phase change battery goes in, self-contained, charges itself, kiss.
Yeah. And no sound, no cooling of the space, no potential for
Nope, no moving
leaks.
parts, no venting. You got it.
Would you still put a leak pan, drip pan on it?
No, I don't know what you're going to catch. Right? So it's a giant. And if you guys watch the video, and I apologize, I would play it, but I want to blow the internet up here for us. If you watch the video on our YouTube, you'll see what I mean. It is very minimal water inside of it. It is a box holding phase change and a heat exchanger.
Yeah, so just the water in the heat exchanger itself that's going through. There is no storage of water.
Yeah, you got it. So it's very, very minimal.
Cool. Alrighty. Well, I'll do one last call for questions. And if not, thank you very much, Michael. And yeah, we'll be taking December off. So we'll be back again in January for kind of next year's rounds of the Passive House Alberta Building Better in Alberta webinar series sponsored by the Alberta Eco Trust. Thank you all for attending today.
Thanks, guys. Appreciate you coming. And as I say, any questions, hit me up on LinkedIn, drop me an email. Happy to help.
Thanks.